Many users familiar with Raspberry Pi often ask me, what's the difference between your product and Raspberry Pi? I'd like to share with you our key differences from both hardware and cloud perspectives. Raspberry Pi is essentially a small computer that runs Linux. It typically comes with 4 gigabytes or even 8 gigabytes of RAM. Powerful, yes, but also more expensive and power-hungry. Our product, on the other hand, is specifically designed for IoT applications, especially for collecting data from various sensors. That means we don't need such high-end hardware configurations. For example, our main controller chip only has 8 megabytes of memory. While it may seem small, it's already sufficient for our intended use cases. Because of this, we're able to significantly reduce both cost and power consumption compared to something like Raspberry Pi. In fact, in hardware design, higher performance isn't always better. What matters most is achieving just the right balance. Overpowered components not only waste resources, but also raise costs, making it harder to stay competitive in the market. Take washing machines as an example. The control chip inside only needs to handle simple tasks. In such cases, we can choose a cost-effective, perfectly suited microcontroller, maybe just a few cents worth. If you were to install a Raspberry Pi in a washing machine, it would be unnecessarily expensive, power-consuming, slow to boot, and potentially less stable than a traditional microcontroller. We chose chips from Espressif Lekun, whose products are easy to develop with and backed by a large community. When issues arise, there's plenty of documentation and support available. Although our main controller only has 8 megabytes of memory, it integrates Wi-Fi and Bluetooth capabilities, giving it solid connectivity. While its specs fall far short of Raspberry Pi, it's actually quite flexible and practical when it comes to programming and application compatibility. In addition, we've added several modules to the development board to help users get started faster and quickly prototype their ideas. Now, let's talk about the sensors, the foundation of any IoT device. To make the user experience easier, we've integrated some commonly used sensors directly onto the board. First, there's the 5MP camera module, based on the OV5640 sensor, supporting multiple image formats. Users can also choose different field of view (FOV) lenses, including wide-angle or infrared lenses for night vision, to suit various scenarios. Next up are environmental sensors. We include a temperature and humidity sensor and a combined temperature and pressure sensor. One thing to note, since the pressure sensor is mounted on the PCB, the measured temperature might be slightly higher than the ambient due to heat generated by the circuit itself. However, if users require more accurate ambient readings, they can connect an external sensor via the green pin header. Then we have the PIR, passive infrared sensor, which detects changes in infrared radiation emitted by moving humans or animals. Its working principle is simple yet effective. When a target with a temperature difference moves into the detection area, the infrared rays are focused by a Fresnel lens onto a pyroelectric sensor. As the target moves, the focal point shifts, triggering motion detection. This makes PIR ideal for security systems. When movement is detected, the system can trigger the camera to take a photo, avoiding continuous video recording and thus reducing power consumption and bandwidth usage. Here's an ultrasonic sensor, which calculates distance by emitting ultrasonic waves and measuring the time it takes for the echo to return, basically time times speed of sound. However, the speed of sound isn't constant. It varies depending on air temperature, humidity, and pressure. These factors significantly affect how fast sound travels through the air. So to improve measurement accuracy, we use the onboard temperature, humidity, and pressure sensors to get real-time environmental data. Then, by referencing pre-calculated values, we determine the current speed of sound and apply it to the echo time to calculate precise distance. This high-precision ultrasonic ranging method is perfect for detecting obstacles or tracking object movements, widely used in security, automation, and robot navigation. Lastly, we have the thermal imaging sensor, capable of measuring temperatures at multiple points simultaneously and generating a corresponding thermal map. One image shows the processed visualization, while the other displays raw data showing temperature readings per coordinate. Thermal imaging provides real temperature measurements, making it crucial for fire prevention scenarios. Compared to video analysis alone, thermal imaging offers much more direct and reliable early warning capabilities. Of course, beyond the sensors mentioned above, there are many others we support, such as CO2 sensors for air quality monitoring, TVOC sensors for indoor air assessment, oxygen sensors, water leakage sensors, displacement sensors for bridge health monitoring, and pressure sensors for weight measurement. In fact, there are likely tens of thousands, if not hundreds of thousands, of different types of sensors available today. Thankfully, thanks to years of industry development, sensor interfaces have become highly standardized. Most sensors either output analog voltage or use digital interfaces like I2C SPI or UERT. This means no matter which sensor you want to use, you can easily connect it to our board via the green pin headers. To help users better understand and integrate these sensors, we'll be releasing a series of tutorial videos demonstrating how to connect various sensor types, expanding your IoT project possibilities. This flexibility enhances the product's adaptability and empowers your creativity. Whether you're building smart home systems, industrial automation setups, or environmental monitoring solutions, you'll find the right sensor and a quick way to integrate it into your project. Once the sensors collect the data, the next step is connecting to the internet and sending the data to the cloud. When it comes to connectivity options, our main controller supports built-in Wi-Fi and Bluetooth Low Energy BLE, allowing easy access to home or office networks and enabling communication with nearby BLE devices. Additionally, we offer an optional 4G module that supports global network standards, ensuring reliable mobile connectivity wherever you are. The included 4G antenna further improves signal reception, even in weak signal areas. For applications requiring more stable and high-speed connections, we've also included an Ethernet port, so you can simply plug in a network cable and enjoy the reliability of wired internet. Let's also talk about LoRa long-range radio. For those unfamiliar, think of it as a special kind of Wi-Fi, but with much longer range, up to 10 kilometers. More importantly, LoRa is extremely power efficient, allowing battery-powered devices to run for years. Of course, it does come with trade-offs, such as slower transmission speeds, usually at the kb level. But for typical IoT data like temperature and humidity, this speed is more than enough. In summary, we offer a variety of connectivity options: Wi-Fi, BLE, 4G, Ethernet, and LoRa, each with its own advantages. You can choose the one that best fits your specific application scenario. This diversity of options expands the product's applicability and gives users greater flexibility. Power supply is another critical aspect of IoT devices. In many real-world applications, continuous power from an adapter isn't possible, so batteries must be used. We support rechargeable lithium batteries for long-term reuse scenarios and also non-rechargeable lithium batteries, which have ultra-low self-discharge rates, ideal for ultra-long life applications. For instance, in container tracking applications where the device must last up to 10 years, non-rechargeable lithium batteries are the perfect choice. Rechargeable ones, even with low power consumption, simply can't match that longevity due to self-discharge. Some scenarios, like fire safety systems, demand even higher reliability. In such cases, we use a dual power system combining battery plus adapter. Normal operation uses the adapter to preserve battery life, and during emergencies when the adapter fails, the battery seamlessly takes over to ensure uninterrupted operation. Our device supports multiple power sources: battery, solar, adapter, or dual battery plus adapter mode. And when using an adapter, the input voltage range is as wide as 3.7 V to 18 VE, enhancing deployment flexibility and compatibility. Through diverse power options, we aim to provide stable, reliable, and sustainable energy support for all kinds of IoT applications. Beyond hardware enhancements in sensors and connectivity, the biggest difference from Raspberry Pi lies in our open-source cloud platform. In the world of IoT, devices cannot be isolated islands. They must be connected and centrally managed. That's why we've invested heavily in the cloud. Our cloud platform goes far beyond basic user device and module management. It includes a host of useful features: OTA firmware updates, remotely update device firmware without needing physical access, online programming and compilation. To lower the learning curve, we've built a web-based coding environment. No USB cables or complex local development environments needed. Cloud log viewing. See device logs directly on the platform, no wiring required, saving lots of debugging time. One feature I'm particularly proud of is our integration with large language models, LLM. This allows users to push sensor data, such as photos or thermal images, directly to AI models for intelligent decision-making. For example, you can upload a picture and ask, "Is someone falling down?" Or send thermal imaging data and ask, "Is a fire about to break out?" We've also opened up a rich set of APIs, both internal and external, allowing enterprise users to integrate their systems with our cloud platform effortlessly. Developers can automate scripts via APIs or even open a small terminal-like interface on the UI to send commands directly to the device. And here's a really cool feature. Since GPIO I2C and SPI protocols are already well standardized, we've encapsulated them into HTTP-accessible virtual I2C/SPI control protocols. What does that mean? When integrating a new sensor, you don't even need to modify the firmware. Just call the Cloud API, and you're done. Sounds convenient, right? In conclusion, our goal is to build a fully integrated hardware plus cloud IoT solution, making it easier for users to get started while also making devices smarter, more flexible, and sustainable. If you're working on an IoT project, give our product a try. It might save you a lot of time and effort, letting you focus more on your ideas and application scenarios.